Today we are going to learn about understanding RNN architectures, simple to LSTM. We'll explore the evolution from basic RNNs to LSTMs, focusing on their functionalities, challenges, and practical applications. By the end, you'll be equipped with the knowledge to select the appropriate RNN architecture for diverse tasks. Recurrent neural networks, or RNNs, are a type of neural network architecture specifically designed to handle sequential data. Unlike traditional feed-forward neural networks, RNNs have connections that form directed cycles, allowing them to maintain a memory of previous inputs. This memory is crucial in tasks where the context provided by prior data points is important, such as language translation, speech recognition, and time series forecasting. The basic structure of an RNN consists of input, hidden, and output layers, with feedback loops from the hidden layer to itself. This looping capability empowers RNNs to capture temporal dependencies in data. As we delve deeper, understanding the foundational aspects of RNNs will provide the groundwork for exploring more advanced architectures. One of the main challenges of using simple RNNs is the vanishing gradient problem. This issue arises during the training of neural networks using backpropagation through time, BPTT. The gradients of the loss function with respect to the model parameters become extremely small, effectively preventing the network from learning long-range dependencies. Mathematically, this problem occurs because the gradients are products of many small numbers, leading them to shrink exponentially as they propagate back through the layers. This makes it difficult for the network to update weights effectively for earlier layers. The vanishing gradient problem significantly hinders the performance of simple RNNs in applications requiring long-term memory, such as language modeling. Solutions like gradient clipping and advanced architectures like LSTMs have been developed to mitigate this issue, enabling more effective learning over longer sequences.
Long short-term memory networks, or LSTMs, are a sophisticated type of RNN designed to address the vanishing gradient problem. Introduced by Hochreiter and Schmiduber in 1997, LSTMs have become a staple in the field of deep learning for sequential data processing. Unlike simple RNNs, LSTMs incorporate a more complex cell structure that allows them to remember information for extended periods. This is achieved through gated units that regulate the flow of information, effectively managing long-term dependencies. LSTMs have a wide range of applications, including language translation, speech recognition, and time series prediction. Their ability to retain information over long sequences makes them superior to simple RNNs in tasks requiring long-term context. Understanding the mechanics of LSTMs will provide you with the tools to tackle complex sequential data problems efficiently.
An LSTM network is built around a key concept, the cell state and the various gates that interact with it. The cell state acts as a conveyor belt that runs through the entire sequence, allowing information to flow unchanged. It is the job of the LSTM's gates to regulate this flow. The forget gate determines which information should be discarded from the cell state. The input gate decides which new information should be added. Finally, the output gate controls the output of the cell state information. These gates use sigmoid activation functions to make decisions based on the current input and past output. By dynamically adjusting the information flow, LSTMs can maintain long-term dependencies in data. Understanding these components is crucial for grasping how LSTMs overcome the limitations of simple RNNs. When comparing RNNs and LSTMs, the most significant difference lies in their architectures. While simple RNNs have straightforward feedback loops, LSTMs incorporate complex structures with multiple gates. This architectural advancement allows LSTMs to manage long-term dependencies much more effectively than RNNs. In practice, LSTMs exhibit superior performance in tasks requiring memory over extended sequences. They are particularly useful in applications such as speech recognition and language modeling, where context is critical. However, LSTMs are computationally more intensive than simple RNNs. While RNNs might still find use in simpler sequential tasks, LSTMs are the go-to choice for complex problems. Understanding these differences will help you make informed decisions when selecting an architecture for specific tasks. LSTM networks have found widespread application across various industries due to their ability to model complex sequential data. In language modeling, LSTMs are used to predict the next word in a sentence, offering applications in chatbots and translation services. They are also prevalent in time series prediction, where they help forecast stock prices and weather patterns by analyzing historical data. Speech recognition systems utilize LSTMs to convert spoken language into text accurately. Additionally, LSTMs are employed in anomaly detection, identifying deviations in data streams for security and maintenance purposes. In industrial automation, LSTMs are used to optimize processes by predicting machinery failures. These diverse applications highlight the versatility and importance of LSTM networks in modern data-driven industries. Implementing LSTM networks is made accessible through several popular deep learning frameworks, including TensorFlow, PyTorch, and Keras. These frameworks provide high-level APIs for building, training, and deploying LSTM models. In TensorFlow, LSTMs can be implemented using the tf.keras.layers.lstm class, which simplifies the process of model creation and training. PyTorch offers a more flexible approach with its torch.nn.lstm module, allowing more control over the training loop. Keras, built on top of TensorFlow, provides an intuitive interface for quickly prototyping LSTM models with minimal code. Regardless of the framework, efficient implementation requires careful consideration of hyperparameters, such as the number of layers, units, and dropout rates. Understanding these frameworks will enable you to leverage LSTM networks effectively for your projects. Choosing the right RNN architecture for your project involves evaluating several factors. The nature of the task is paramount. Tasks requiring long-term memory and contextual understanding are better suited to LSTMs. The characteristics of your data, including sequence length and complexity, also influence the choice. Resource availability, such as computational power and time constraints, may affect your decision, as LSTMs are more resource-intensive than simple RNNs. Lastly, consider the trade-offs between model complexity and performance. While LSTMs offer increased capabilities, they also require more data and tuning to optimize performance. By weighing these factors, you can select the most appropriate RNN architecture to meet your project's needs.
In this video, we've explored the evolution of RNN architectures from simple RNNs to the more advanced LSTM networks. We discussed the challenges faced by simple RNNs, such as the vanishing gradient problem, and how LSTMs address these issues with their sophisticated cell states and gating mechanisms. Understanding these key concepts is crucial for optimizing sequential data processing tasks across various industries. The choice of architecture can significantly impact the effectiveness of your projects, making it essential to consider factors like task requirements and resource availability. As you continue your learning journey, experimenting with these architectures will deepen your understanding and enhance your ability to tackle complex data challenges.